Hello, in this video we're going to be deriving the Lewis relation. So the first thing we have is we have the Nusselt number. That is equal to the heat transfer coefficient multiplied by its length d over its thermal conductivity, K. That is equal to its coefficient A, the Reynolds power to the B, and the Prandtl to the C. We also have the Sherwood number. That is equal to its mass transfer coefficient multiplied by its length d over its diffusion coefficient DAB. Now, we know that is also equal to the A, coefficient A, multiplied by its Reynolds number to the B, and the only difference is the Schmidt number to the C. We know that A, B, and C can be solved experimentally, and that if we use either method in an experiment for the Prandtl or the Schmidt number, we would find the same values. So we know that the Prandtl and the Schmidt number are the same. So we can also say that the Nusselt over the Sherwood number is equal to that. So we know the Prandtl. We also know that the velocity in this problem doesn't matter because the Reynolds number cancels out. So for the Prandtl number, we have its velocity over its thermal diffusivity. We have the Sherwood number, its velocity is equal to its diffusion coefficient. We know that the velocities cancel out, and all we're left with is the diffusion coefficient over its thermal diffusivity. We can also say that this is also equal to the 1 over the Lewis relation. And in the problem that relates to the dry and wet bulb, we can also say in moist air that the density multiplied by its heat capacity multiplied by its diffusion coefficient over its thermal conductivity is equal to the 1 over the Lewis relation. And going back to the original two equations, if we use the left side of the equation, we do the Nusselt over the Sherwood number, we can see that the heat transfer coefficient over the mass transfer coefficient multiplied by its thermal conductivity, and we also know it's multiplied by its diffusion coefficient. And as you can see, the length d isn't in here because they cancel out. So we know that DAB over K, we have a DAB over K here, and we have a DAB over K here. We know the 1 over the Lewis relation, that is equal to 1. We also know this is equal to 1 over the Lewis relation to the C, because we're doing the right side of the equation now. We can see that 1 over the density multiplied by its heat capacity. So we know that the 1 over the Lewis relation, we know that's equal to 1 in moist air. So we can say that DAB over K is 1 and DAB over K is 1. And we can substitute this, the 1 over the Lewis relation, for its volumetric heat capacity. And that is equal to its heat transfer coefficient over its mass transfer coefficient. So this equation, its heat transfer coefficient over its mass transfer coefficient, is equal to the volumetric heat capacity. That is equal to the Lewis relation.